Well, hello there, Mr. Bucko here with some information about 45, 45, 90 triangles. I have one on the screen here called ABC, and we know that this is a 45, 45, 90 triangle because I used this software here to measure these angles. So angle BCA right here is 45 degrees. Angle ABC, this one right here, is also 45 degrees. And angle BAC right here is 90 degrees. So there's no doubt that this is a 45, 45, 90 triangle because these measurements are indicating that they are. So that's what it's going to be. And you'll notice here that if I manipulate this triangle, make it smaller or bigger, notice that these three values will always stay the same. So as I move this around, you'll notice that the angle measures stay the same, that this will always be a 45, 45, 90 triangle. So the side lengths change, but the angles don't. So now we're going to focus on those side lengths here. So I measured the side lengths too. Side length AC, this one right here, and right now it's 7.27 centimeters. And so is side length AB, and you'll notice that those are the same, and you'll also notice that when I change this, that those values always stay the same. And the reason why is because it's a 45, 45, 90 triangle, and as a result of that, it's an isosceles triangle. So these two side lengths right here will always be the same in a 45, 45, 90 triangle because it's isosceles, and that's how those work. BC in this case is now 12.42. I did the measurement there. That's how big it is. And you'll notice that when I change this, that side length changes as well. Now it's 9.61. If I make it bigger, it can go up to 14. It's going to go all over the place. You'll notice that this value is not always the same as these two, but that these two values will always be the same. The relationship we need to focus on here is the fact that this length right here, the hypotenuse of the 45, 45, 90 triangle, is always equivalent to the side length of one of the legs, which one, it doesn't matter because they're the same, times the square root of 2. So this is the relationship we want to focus on in a 45, 45, 90 triangle. That one of the side lengths, in this case I picked AB, but I could have easily picked AC because it's exactly the same. So I took AB, I multiplied it by the square root of 2, and you'll notice the value I get is exactly the same as the measurement of BC. And you'll notice now that no matter how I manipulate this triangle, this 45, 45, 90 triangle, these two values always stay the same. Why? Because the relationship of the hypotenuse to the legs in a 45, 45, 90 triangle is always times the square root of 2. So these will always stay the same. And therefore, if we know the length of one of the legs, all we have to do is multiply it by the square root of 2, and we'll get the length of the hypotenuse. And then if we know the hypotenuse, we know that that's equal to the length of one of the legs times the square root of 2, and we can do some reverse algebraic work there to figure that out. Now up in the corner, I have this stuff here. This is just the Pythagorean theorem. This is just saying that a squared, in this case I'm assigning this length AB to be a, plus b squared, b in this case is AC, this equals what we're calling c squared, and here's c squared right here, BC, which is right there. So you'll notice that these two values, the 160.81, 160.81, when I change the triangle, those values stay the same as well, because this is the Pythagorean theorem. That's what's happening right there. Those values stay the same because this is a right triangle, and the Pythagorean theorem is always true for right triangles. So the focus here is that the hypotenuse of a 45, 45, 90 triangle is the length of one of the legs times the square root of 2. And that we can see right here.